All right, our next speaker, Veda Shankar. The title is Taming Billions of LIDAR Points with GPU Database.
Today we'll talk about how we, Tahoe project, where we use LIDAR data to actually, basically study like the intermix of wildland and urban area, and we'll try to build a better fire model. And we're going to be using an open source platform called OmniSci. We just went through a name change from MapD to OmniSci about a couple of weeks back. And if I can give a good explanation if you want to talk about it at lunch. And what I'll show here is how we ingest all these LIDAR data into OmniSci and then render this massive data set visually. Because one of the interesting things, before I go further, let me introduce myself. I'm Veda Shankar. I'm with OmniSci. My task is to help build the MapD or OmniSci community, and worked with Mike Flaxman, who is enjoying in Palm Beach right now, or rather Palm Springs, for the Cal GIS. He's actually the lead on this project. He's a GIS expert. So one of the common themes that I've noticed in the last couple of days at this forum is everybody is talking about data and the science for managing that data. When you want to extract value from data, whether it's biomedical, urban planning, or energy research, you need compute power. And this is a chart where it shows typically an Intel or an AMD CPU, its year-over-year performance growth versus the growth in data. And clearly there is a huge gap between the two. We think that gap is going to be narrowed or by GPUs. So I don't know, how many of you use GPUs in your R&D? Okay, I see quite a few hands, and that's very encouraging. And surely like machine learning and AI, they are embracing GPUs. Precisely as this graphic shows, we can do, even though CPUs are more capable, they can do like one task in a nanosecond versus a GPU, which takes 10 nanoseconds per task. But the very fact that we have thousands of GPU cores versus tens of CPU cores, we can actually achieve far greater, almost like 200 times more number of tasks per nanosecond. So similarly, if you look at this memory bandwidth chart, so the bottommost layer, you have the 7.2K RPM SATA drives, which are primarily used for creating your data lakes, right? And then you have the SSD layers that could be your flash, NVRAM, and things like that. But typically giving you about 1 to 2 gigabytes per second. And then on top of that, you have the CPU memory, system memory, and that's about 120 gigabytes per second tops, right? But then when you look at the GPU memory, that's all the way in terabytes per second. So in orders of magnitude, it just, the rest of the memory speed or bandwidth just pales in comparison. The only thing is GPU memory is premium, right, compared to the amount of memory that is available. So at OmniSci x MapD, we harness this power of GPU, and we have built a database and an analytics platform ground up. It has come from MIT research. Our CEO's PhD thesis was this GPU-based columnar SQL compatible database. And so it has been built up to kind of harness both the multiple cores, the thousands of cores that are available, and also the memory bandwidth that's available in GPU. And what we have done is we have actually optimized some of the SQL analytics operations, which are basically the where clause, right, which is your filtering, and the segmenting, which is group by. So we actually pre-compile a lot of that those query plans so that they can run very, very fast. Now, even though we are optimized for GPU, you can also test OmniSci on any CPU-based platform. You can, in fact, run it on your laptop. Because what we use is a just-in-time compilation, so you can actually run it either on CPU or GPU. Obviously, your performance is going to be, orders of magnitude, better on a GPU. Now, what we realize is we can run these SQL queries really fast. We have optimized this. We try to vectorize all these queries so that they can run in parallel. But the results are sitting in GPU memory. Now you can easily then attach it to the graphics pipeline of the GPU, because the primary purpose that GPU was invented was because of graphics rendering. So without kind of bouncing the data between CPU and GPU, we can actually make use of the GPU memory to render the graphics and instantaneously. We use something called as a Vega rendering spec. It's actually a JSON file that you specify your query, the data section, and then you describe in that how you want to basically render that data. And so if you look at this architecture diagram, you have the SQL engine at the bottom, and then the Vega-based rendering engine, and then we have Immerse, which is our browser-based platform. And and you can actually ingest the data at rest from S3 or from your local file system, or it could be coming from Kafka, Scoop, Thrift, any of those mechanisms. We can also talk JDBC, ODBC, Python APIs. How many of you use Tableau for your analytics? I see quite a few hands. Now, if you're comfortable with Tableau, which a lot of people are, you could still use your Tableau, but then use OmniSci as your backend SQL. Now, suddenly from dealing with millions of records, you can actually go to billions of records. I've heard a lot of speakers. In fact, I'd be very interested in talking to all those people who talked about tweet maps and analyzing it. OmniSci was actually born out of analyzing tweets during the Arab Spring. So our CEO and founder, Todd Mostak, was doing his PhD at MIT, and he was analyzing all the tweets coming out of Arab Spring, and he just could not find a single database that actually was able to handle the billions of tweets coming out. So guess what he did? He wrote a database running on GPU, and we have an amazing demo on our website, which actually will show you how to analyze tweets, and you can do that in real time. So before I go further, I'm going to quickly show you a demo just to show you the power of using GPUs. Now, there's a very similar demo that's also available for tweets. So this is a case where we have basically 1.1 billion taxi trips in New York from 2009 to end of 2015, and it's a large data set with about 44 columns. So it's not like just 2 columns, right? So we have like pickup point, drop-off point, what borough, how much tip, la la la. There's so many of that. So this particular one actually is a little bit unique because I wanted to show you also the geospatial capabilities of that. So you have 1.2 or 1.1 billion records of taxi trips intermixed with 1 million polygons of Manhattan buildings, or actually New York City buildings. And I can actually zoom in, and you will actually see that the number of records will actually change. Okay, it's slower than what I thought. Okay, but let's do a very quick analysis. And what we find is because we are Python compatible, we actually, along with H2O, which is used in machine learning library, we actually formed something called as Go AI, where we actually use the GPU data frame. So you can keep your data in OmniSci, download it into your pandas data frame, run some filtering operations, visualize it, and then you can do some feature selection and then use that data frame to pass it on to H2 or XGBoost to do your analysis. So here we'll do a very quick visual analysis. What you have on this line chart is the pickup dates and the tip percentage. So what you notice that every year around Christmas time, the tip percentage, actually there's a kind of a nice sharp fall. So is it because people are becoming frugal during Christmas? Any ideas, any thoughts?
They're getting cash instead.
Oh, amazing. Yes, sir. So you don't need to analyze. So one way to do that is if you look at the histogram of all the tip percentages, you notice that there's a nice peak around 20%, which is what we would expect. But then there's also a very large spike around 0%. So if you just drill down, I'm going to just zoom into all the 0%ers. And what I notice is that the count by payment actually became, actually let me unfilter that. Yeah, so which is exactly right. So it's mostly cash payment. So the taxi drivers were not reporting the tips. But what you just notice is as I selected this tip percentage, immediately that SQL query was applied to all the billion records for every single chart. So you are actually this is what we call as cross filtering. And if you notice, this is actually working off of the internet over Wi-Fi, and who knows who else is using this, but it was pretty snappy. But you can go through a billion records like that. Now, if you want to confirm this, what you can do is I can simply click on the cash payments, and you will suddenly notice that, hey, pretty much people are paying 20% when they're using credit card, and you see this big spike in the usage, and that's because that's when the credit card system was introduced. Anyway, there's more to it. I need to jump to the next, back to my LIDAR data. So LIDAR, as you know, is light detection and ranging. It gives you lots of millions of points or even billions of points to create a 3D point cloud, to kind of describe the surface, the height, or the depth. Now, we think a GPU-based database is ideal for such an application because you can handle this huge volume of data and visualize it, interact with the data. And right now it is kind of very problematic, and a lot of LIDAR data has been collected, but people are not able to kind of put it to good use. We support geospatial features. This year we introduced support for geospatial features, so you can support point, line string, polygons, multi-polygons. Also you can import Esri shapefiles, GeoJSON, CSV for getting your data in. You can also do all kinds of geometric or geospatial functions using SQL. Right, so you could do your ST contains, ST distance, and to the the backend database. We support actually Web Mercator, but everything is stored as EPSG 4326 as longitude, latitude. So you need to convert it into 4326 when you bring the data into OmniSci. And what we found was PDAL library, which is again open source, was actually one of the best or easiest ways to kind of ingest the LIDAR data into OmniSci. And it does the conversion for you. And the PDAL actually is available both through like a command line deployment through Conda, or you can use it as a Docker image. And so in the slide, you'll see how I've used a Docker to convert your LAS files into CSV files and apply the reprojection and conversions into a format that is suitable for OmniSci. Here is actually a command line method of using a PDAL. So I'm going to, you have these slides, I've already given it to the organizer, so you should find it on the website. There's a Jupyter notebook that actually has in detail how to walk through converting your LIDAR data, raw LIDAR LAS files into CSV and ingesting into Omni. Talking about Lake Tahoe, it's a beautiful national park. I don't know how many of you have seen it, but also it has 50,000 buildings. One of the problems is, having trees or, greenery which is tall. It acts as a fuel ladder. So wanted to quickly do basically a mapping. And in this particular case, I know I have like exactly 2 minutes. So you have like 42 million points of data. Here we have data from LIDAR and also from the buildings. So the color over here basically represents the height of the tree, and the yellow multi-polygons that you see, they are the buildings. So if I were to click on the tallest shrubbery over here, you will notice that these are the buildings that are very close, and I can actually zoom in to that. Since there's only 2 minutes left, I'm going to leave you with that visual, and I'm open for Q&A.
Yes, the ingestion and the conversion of the LiDAR data to CSV using PDAL, does that run on GPU, and how long does that take?
Excellent question. That will run on CPU.
CPU.
Yeah. But once it's converted into CSVs, off you go.
Okay.
Yeah. Good question.
Well, thank you very much. It was a great talk.